Okay, I welcome you all for my next session on D flip-flop. Okay, D flip-flop. So we will be describing about all the parameters of our D flip-flop. So first we will start with why this flip-flop is required. Then we will be drawing the circuit diagram or the logic diagram, and we will be explaining about its operation. Then we will be drawing the truth table, that is the extended truth table. We will be drawing our extended truth table. Then finally we will be going with our characteristic equation as well as the characteristic equation. So the third thing is here characteristics equation, and finally the excitation table. Clear? So these are the things that we are going to see with respect to D flip-flop. So first of all, why this D flip-flop? And first of all, what is called as this D stands for? So D, sometimes they will be calling this as a delay flip-flop, or sometimes this will be called as direct flip-flop. Okay, or sometimes they will be calling this as a delay flip-flop or direct when the flip-flops. So why delay means whatever the input that you are going to give, that will be delayed after a fraction of second, then you are getting your output side. Or whatever the input that you are going to set here, that input will be your next state condition. So this is also called as direct flip-flops. And why this D flip-flops? So when you talk about why this D flip-flop means, so in our SR flip-flop, so those who have not seen my previous video, you can check my video in SR flip-flop. So in our SR flip-flop I have 4 states starting from 0 0 0 1 1 0 and 1 1. For each state I have an next state condition, whereas for 1 1 condition alone I am not having any output. So for 1 1 it is nothing but your indeterminate net form. But if I want only 2 conditions, that is either a set output or for a reset output, I want to go for a flip-flop that is called as a D flip-flop or direct on the flip-flop. Okay, so here I will get my output either as a set output of 1 or as a reset output of 0. So if you want only 2 outputs, either a set or reset condition, only the 2 condition, we are going for this D flip-flop. Okay, so now we will go with the logic diagram. Okay, logic diagram or circuit diagram of this D flip-flop. So this is nothing but the extension of your SR flip-flop. So just I am going to draw my SR flip-flop. Okay, so just I am going to draw my SR flip-flop. So we know that, so this is nothing but your cross-coupled configuration, which means that Qn is connected as an input at this point. We are having the Qn, and here I have my Qn bar. Qn bar will be the input at this one of the end, and here we are supposed to find the next state, that is Qn plus 1, and here it will be Qn plus 1 the whole bar. Okay, so in front we will be having one more NAND gate, and both of these NAND gates are connected with a clock pulse, and already we are setting your clock as 1. So in the previous thing, the same diagram we have drawn for our SR flip-flop. So what is the difference? The previous thing, if this is want to become an SR flip-flop, this for example this is your first gate, second one, third and fourth. So this is nothing but your S term, and this is nothing but your R term for your SR flip-flop. But now this is not called as an SR flip-flop. Now this will be a D flip-flop. So in order to make this D flip-flop, what I am going to do here is, just I am going to connect both the inputs to a NOT gate. Okay, so another input I am going to connect to a NOT gate, and I am going to set the input at D. So if this is delta D, this will be nothing but a D bar. Okay, so one of the input for your NAND gate is D. Another input for the NAND gate number 2 is also D bar. Okay, other input for the NAND gate 1 is clock, which is nothing but 1, and another input for the bottom NAND gate 2, this is also nothing but 1. So you have one of the input as 1, another input as D bar, another input as 1, another input as D. Okay, so based on the output that is coming out from the gate number 1 and gate number 2, your Qn is going to, that is Qn plus 1 is going to depend. So already we know that if there is a single input, that is now I have only one input, that is D is a single input. Okay, if D is a single input, D can take either a 0 value or 1 value. Okay, D can take either 0 value or 1 value. Clear? So if D takes a 0 value, what will happen? Okay, if D equal to 0, what will happen? So I am now setting the D value as 0. So automatically my D bar will be equivalent to 1. So what will happen? So one of the input for here gate number 2 will be 1. Other input for the gate number 1 will be 0. So what will happen now? So when you check the output at gate number 1, what is the output? Similarly, output at the gate number 2 will be what? So 0 into 1, 0. 0 complement will be 1. Here 1 into 1, 1. 1 into 1's complement will be 0. Okay. So here what I am getting? Here I will get as 1. Here I will get as 0. Okay. Now I am going to check the output at gate number now 3. 3, which is nothing but what? Qn plus 1. What is the thing we want to check? Similarly, if I get the value, I don't want to go with the bottom bar. Output at gate number 4, which is nothing but Qn plus 1 the whole bar. So what will happen? So one of the input is Qn bar for the Qn. So this will be Qn bar the whole bar. So which is nothing but Qn. I am not getting any value. Okay, Qn I am not getting any value. So what I am going to do? I am going to proceed with your bottom side. Okay, I am going to proceed with your bottom side. So in the bottom side, one of the input is 0, other input will be Qn, the whole bar, which is nothing but 0, 0 into anything 0, 0 complement, so this will be 1. So if this is 1, definitely my Qn should be equivalent to 0 based on this concept. Okay, so now if you draw the truth table, okay, if I draw the truth table, so one of the input is D and your Qn, I want to find my Qn plus 1. So if this is 0, irrespective of this thing, what is happening to your Qn plus 1? So Qn plus 1 will be also equivalent to 0 because Qn should be 0, which means that my Qn is nothing but here, that is equivalent to 0. Now what happens if I change the input as 1? Okay, so for this we are going with another one color to make it very clear. Okay, so now I am going to change the input as now 1. So if this is 1, this is the input will become 1. So automatically if this is 1, D bar will be 0. Okay, D bar will be 0 means one of the input for your D bar will be in, now it became 0. So 1 into 1 is 1, 1's complement, now it will become 0. So when you talk about the back side, 1 into 0, 0, 0's complement, it will become 1. Okay, now we want to check the output at the bottom side. When D equal to 1, what will happen? When D equal to 1, so the same procedure I am writing. Output at gate number 1 and will be what? Output at gate number 1 will be 0. Output at gate number 2 will be 1. So what will be your next thing? So output at now gate number 3, which is nothing but Qn plus 1. Similarly, output at gate number 4, which is nothing but Qn plus 1 the whole bar. So if you talk about Qn plus 1, this is nothing but 0 into qn bar the whole bar, 0 into qn bar the whole bar, which is nothing but that 0 and anything is 0, 0 complement will become 1. Okay, directly I am getting the value as 1. So I no need to proceed with the next word. So what is my qn plus 1? Qn plus 1 will be equivalent to 1. Clear? So irrespective of this thing, if the input is 1, that is if d equal to 1, my qn plus 1 is also going to become 1. Okay, clear? So now I got two conditions. One is for the reset condition, another is for a set condition. So what is the reset and set? That is when d equal to 0, I am getting my next state qn plus 1 as 0. This denotes that this is nothing but a reset operation. Similarly, when d equal to 1, my qn plus 1 is going to become 1. So this is nothing but a set condition. Clear? So now I am going to draw your next thing, which is nothing but what? Extended truth table. Okay, I am going to draw your extended truth table. So how you will draw your extended truth table? So one of the input is your d input, and qn I am going to now expand it. Okay, qn I am going to now expand it. So when you expand your qn, so qn can be either 0 or 1 for your input as 0. Similarly, for the input as 1, qn can be either 0 or 1. So when d is 0, I am not going to worry about the present state, that is qn. So when d is 0, always my next state is going to become 0. Similarly, when d is 1, I am not going to worry about the present state. My next state is always going to become 1. My next state is going to become 1. So this is nothing but the extended truth table. This is nothing but your extended truth table. So based on this extended truth table, we are going to write my characteristic equation, okay, or your logic equation. Okay, so what is this characteristic equation? So how we can form? So we can write this characteristic equation, which is nothing but here qn plus 1 using your k-map. So now there are only two variables. So I am going to draw here on the k-map, which is having one of the input as d, another input as qn. This can be either 0 or 1. This can be also either 0 or 1. So what is happening? So when d is 0, where you got your output? Got my output in only two locations. That is when d equal to 1 and d equal to 1 and qn equal to 0, and d equal to 1 and qn equal to 0, my output will be 1. When d equal to 1 and qn equal to 1, okay, and d equal to 1 and qn equal to 1, I am getting here output as 0. Okay, so this is nothing but the thing. Okay, where you got the thing, that is for here when d equal to 1, okay, sorry, when sorry here. So when d equal to 1 and qn equal to 0, so this means that this here is a mistake over here. So this will be erased. So when d equal to 1 and payment అయిపోయింది
పేమెంట్ అయిపోయింది.
So now if d equal to 1 and that is d equal to 1 and qn equal to 0, we will have your next status 1, and similarly when d equal to 1 and qn equal to 1, I am having my next status 1 here. So automatically we will have a structure like this way. So if you go by this way, this is nothing but sorry. So I am going with the red color for our better understanding. So if you see, so I will be combining like this. So this is nothing but here D operation. So what will be my next state? So your Qn plus 1 is nothing but D. So automatically we know that. So whatever the D is there, that will be coming in my next state condition. Whatever my D is there, that will be coming in my next state condition. That is when D equal to 1, my next state is also 1. When D equal to 0, my next state is also becoming 0. So this is nothing but my characteristic equation. So now characteristic equation has been completed. So final thing what we are going to see is nothing but here excitation table. Excitation table. So I have already told in my previous lecture what is called as an excitation table. So excitation table denotes nothing but based on my present state and the next state condition how I am going to set my mandatory inputs. Okay, based on my present state and next state condition how I am going to set my mandatory inputs. Okay, how I am going to set my mandatory inputs. So here present state is what? Your present state is nothing but Qn. So your present state here is nothing but here Qn. And what is my next state? Your next state is nothing but here Qn plus 1. Okay, so based on this present state and the next state, based on this present state Qn and your next state Qn plus 1, I am going to determine what is the mandatory input of D. Okay, what is the mandatory input of D? That is what the D will value. That is D is either 0 or 1. So how to form this? So I will be writing your present state and the next state. So present state is on the Qn, your next state is Qn plus 1. So I am going to determine what is the mandatory input D. So already we know that if there are two things, that is one is present state and another is next state, definitely there will be four combinations. Definitely there will be four combinations. That is 0 0, 0 1, 1 0 and 1 1 condition. Okay, now what you want to do? So after completing this table, we want to go with our extended truth table. We want to go with our extended truth table and you want to check where this condition is going to occur. So where you have here present state and next state, we want to check it. Okay, so where is the present state and next state in the extended truth table? So when you see here for 0 and 0, the mandatory input is nothing but 0. Okay, so for 0 and 0, the mandatory input is 0. So for 0 and 0, the mandatory input will be 0. So next condition. So present state should be 0 and the next state should be 1. This is the next condition. Present state is 0 and next state is 1. So for 0, 1, as the present state as 0 and next state as on the 1, the mandatory input is what? 1. Okay, the mandatory input is 1. So now I am going with the next set of combination. Okay, so in the next set of combination is what? It is 1 0. So 1 0 is going to occur in this location. On this location I am having here 1 0 condition. Okay, so that is present state as 1 and the next state as 0. Okay, so for 1 0 condition, the mandatory input what we have for the value of D is nothing but 0. Okay, so what the value I am having is 0. So for 1 0 condition, the mandatory input is becoming 0. Okay, and finally now we are going with the final condition. That is both your present state will be 1 and next state also will be 1. So when both your present state is equal to 1 and next state equal to 1, that is Qn equal to 1 and Qn plus 1 is also going to become 1, means both are becoming 1, the mandatory input. So what is the mandatory input when both are becoming 1 is 1. Okay, both are becoming 1 is 1. So now if you see, okay, now if you see, this is nothing but here excitation table. So here the excitation table, if you check, if the present state both are 0 0, 0 1, 1 0 and 1 1, okay, so whatever the next state is there, that will be here our mandatory input condition. So here also, like your previous thing, what you can do, directly I can write your excitation table, because this is going to depend on here only. Your Qn plus 1 is directly reflecting in here D tab. Okay, 0 means 0, 1 means 1, 0 means 0, and 1 means 1, because here I am 0 1 0 1 condition. So whatever the next state is there, that is coming in our part. Okay, so this is nothing but here excitation table concept. Okay, so now we will have a glance how this is going to work. Okay, so here if you see D flip-flop, a direct flip-flop or a delay flip-flop, so where you are getting your direct output, and why this is called a D flip-flop. Already I have told you why this is called as a D flip-flop, because here instead of going for 4 different state condition, if I want only either 2 state condition, either 0 or 1, that is either a set condition or the reset condition, I no need any type of complex on the circuit. So I want only 2 sets, 2 outputs, either a set output of 1 or the reset output of 0. I am going for this D flip-flop. Okay, so here if you see the logic diagram of your D flip-flop, the logic diagram looks similar to your SR flip-flop. Okay, so those who have not seen the SR flip-flop, you are ready to check with your SR flip-flop. So what is the difference between your SR flip-flop and J flip-flop is only this point. Okay, so only this point I will mark in yellow color. So what are the difference? So only the change is in this region, that is in the green color. I am only going to change, focus it, so that here I am going to add one more extra clock pulse. I am going to add one more extra clock pulse. So this clock pulse that is not a clock pulse, I am going to add one more extra NOT gate. Okay, so in this NOT gate, instead of adding like this way, here everything we are using a NAND type of configuration. So you can also draw like this also. Okay, in some circuit they will be drawing like this way. So this is also a NOT gate, this is also a NOT gate. So any type we can use it. But anyhow, whatever the NOT gate, that is NAND type NOT gate or NOT type NOT gate, what we are going to use it, everything is going to produce a complement output only based on the input. If you are 0, it will produce as 1. If it is 1, it will produce at 0. Okay, so that is the thing. So here now I am making a connection at your S and R. In between I am going to connect, make it as a single input, which will be connected through one NOT gate. Okay, which will be connected through one NOT gate. What is going to happen? So whenever your D input is becoming high, it will be high is going to the top side, that is to the gate number 1, but the low input will be gotten to the bottom side, that is to the gate number 2. Okay, if it is 0, at the top side you will get 0, bottom side will get 1, because in between there is an inverter. Okay, so based on that we have discussed the operation. So if you see the operation, I have explained to you very clearly, that is when D equal to 0, output at the gate number 1 is going to become 1. At the same time, output number, the gate number is going to become, gate number 2 is going to become 0. The same 1 and 0 are feed as the input for the gate number 3 and 4. Another one input for the gate number 3 is Qn bar. So when you apply that thing, 1 into Qn bar, the whole bar, which is nothing but Qn, since I am not having any value at the top side, I am focusing at the bottom side, output at the gate number 4. So where one of the input is 0, another input is Qn. So when you take the NAND operation on the 0 and Qn, you will get 0 complement is nothing but your 1. So since I get here Qn plus 1 as 1, automatically Qn plus 1 should be equivalent to 0. Okay, so this is the thing what we are focusing here. So now if you see, when input of D equal to 0, automatically my Qn plus 1 is going to become 0. Automatically my Qn plus 1 is going to become 0. Okay, so similarly I am going to focus for when D equal to 1 condition. So here also the output at the gate number 1 is going to become 0, output at the gate number 2 is going to become 1. So which means that output at the gate number 3, if you take 0 into Qn bar, the whole bar, which is nothing but directly 1 I am getting the value. 0 complement 0, 0 complement is 1. So if this is 1, definitely I don't want to proceed at the bottom side. So which means that d equal to 1, my qn plus 1 is going to become 1 condition. So what is happening here? Whatever the d value that is coming in here, qn plus 1 value. Whatever the input is there, that will be my next state condition. Okay, that will be my next state condition. So when you derive here truth table, that is extended truth table also, I will get the same thing. If d equal to 0, next state will be 0. When d equal to 1, next state will be 1. So that will be written in the term of logical expression, that is qn plus 1. So qn plus 1, that is the next state condition, is nothing but here or d condition. Clear? So next state condition is nothing but here d condition. So this is the simplest form of flip-flop, where I am going to focus only on two states, either it is a present state or the next state. And already we told you why we are going for this excitation table. So so the excitation table is mainly used for here conversion purposes. Okay, so when I want to convert any one type of flip-flop to other type of flip-flop, that is when I want to convert your D flip-flop to JK flip-flop or T flip-flop or SR flip-flop, still now we have seen only what is called as SR flip-flop. We are not focused on JK or T. So in this class we have discussed about D flip-flop. So similarly, other two more flip-flops will be discussed in the upcoming videos. So if you want to convert any flip-flop to any other type of flip-flop, then excitation table is mandatory. So here we are drawing this excitation table. So excitation table shows based on your present state and the next state, what is the mandatory inputs that you want to set. Okay, so here it is going to focus on your extended truth table. So if it is 1 0, I am getting as 0. Okay, if it is, that is a present state and next state, you want to check it here. So here if you see present state and next state is what? Present state is 0, next state is 1. So if it is 0 1, what is the mandatory input? Mandatory input is 1. So that is the thing I am only focusing here. So if it is 0 and 1, present state and next state is 0 and 1, my mandatory input is 1. So here also you can simply remember for the gate type exams. So whatever the next state is there, that is coming directly in my as a D input. Okay, so I thank you all for your patient listening of this on the video. In the next video we will check about what is called as JK flip-flop.